On a calm November night in 2025, something happened in a backyard that would echo through astronomy communities across the planet. A man named Paul Craggs, an amateur astrophotographer with a modest Dwarf 3 telescope, aimed his lens at a patch of sky where a now famous interstellar object called 3I-ATLAS was expected to be passing. Like thousands of others before him, Paul wasn't expecting much. Maybe a faint smudge, a glowing blur, the kind of dusty comet trail that's been observed since the invention of the telescope. Instead, he captured the sharpest, most defined image of 3I-ATLAS to date, and what it revealed defied everything the professional community had previously shown. The photograph, when viewed in full resolution, immediately stood out. There was no hazy blur, no loose dust cloud or trail-like fuzz. Instead, the image showed a precise, structured silhouette, a bright white central core enveloped in a soft, nearly uniform blue glow that wrapped around the object in a manner no comet has ever displayed before. For a moment, it didn't look like a comet at all. It looked like a machine. This wasn't just sharp. It was uncomfortably sharp. While NASA's official imagery from observatories like Hubble and the James Webb Space Telescope presented 3I-ATLAS as a blurred nucleus shrouded in gas, Craggs's telescope, a consumer-level rig available to hobbyists, showed clarity that cut through the noise. The object had edges. The light had intentional structure. The glow didn't scatter. It cohered. Craggs initially hesitated to post the image. He double-checked his equipment for glitches. He cleaned his sensor. He restacked his data. But each time, the same shape emerged. When he finally uploaded the image to a small astronomy forum, it exploded across amateur science networks like a digital wildfire. Within 12 hours, Reddit threads, Discord groups and astrophotography collectives across the internet were analysing, enhancing and trying to debunk it. Some dismissed it as a fluke. They said it was over-processed, or perhaps the result of an optical illusion, or motion blur from long exposures. But Paul had used industry-standard stacking techniques. Others said it had to be a sensor error, perhaps a bad calibration frame or a light leak. But soon, other backyard astronomers around the world began to replicate the results. From Spain to Australia, images started surfacing that looked eerily similar to Craggs: clean edges, white-hot centres, and a soft blue aura. While the angles and brightness varied, the fundamental structure remained consistent. That's when the real questions began. Why would a $400 telescope resolve something that billion-dollar satellites blurred out? Why had NASA not mentioned anything about this symmetry, this structure, this glow? Was the professional community intentionally avoiding something? Or was this a case of simple oversight, illuminated by chance and curiosity? The photograph reopened the entire narrative surrounding 3I-ATLAS. It forced scientists, commentators and hobbyists alike to ask the forbidden question: is this even a comet at all? More than just an image, Craggs's photograph became a rupture in the official story. Because if what he captured is real, and all evidence now points to that being true, then the nature of 3I-ATLAS must be fundamentally reconsidered. The photograph doesn't just show a visitor from another star system, it shows a visitor with structure, with coherence, with features that might not be natural, and it all began with a single, quiet click in someone's backyard. To understand why the image of 3I-ATLAS shocked so many people, you first have to understand what comets are supposed to look like, and more importantly, why they look that way. Comets, by definition, are chaotic. They are often called dirty snowballs, and that term is surprisingly accurate. These icy objects are made up of frozen gases, rock, dust, and volatile materials left over from the early formation of a solar system. When a comet travels through deep space, far from any heat source, it remains inert, a cold, silent, ancient relic. But as it approaches a star like our Sun, everything changes. The solar radiation begins to warm the comet's surface. The heat doesn't melt it in the traditional sense because there's no atmosphere out there to allow for liquid water. Instead, the ices sublimate. They skip the liquid phase and turn directly into gas. This process creates jets of vapour and dust that burst from the surface, forming the coma, the glowing spherical cloud surrounding the nucleus, and the tail, which is pushed away from the Sun by solar wind and radiation pressure. This process is unpredictable, messy, and inherently asymmetrical. That's why nearly every photograph ever taken of a comet shows something jagged, scattered, and uneven. The tail curves, breaks, or sometimes splits. The coma flickers and reshapes itself. Jets shoot out at random angles depending on the orientation of the comet's surface and how it's spinning. In short, comets are defined by their chaos. Now compare that with what Paul Craggs captured. The image of 3I-ATLAS didn't show a broken nucleus surrounded by asymmetric vapour trails. It showed a sphere, a defined shape, not merely bright, but glowing with a symmetry that comets simply don't exhibit. The core was brilliant white. The glow surrounding it was soft, blue and uniform. Most notably, there was no visible tail, no directional flow of dust or gas, just a compact radiant structure hovering in the dark, looking more like a miniature plasma star than an icy rock from another solar system. This should not be possible. Even the best-behaved comets, those with highly stable trajectories and rotation periods, never display that kind of symmetry. The surface of a comet is always irregular. It has dips, ridges, cliffs, and fractures. As it spins, different parts of its surface are exposed to sunlight at different times. This leads to uneven heating, which leads to uneven sublimation, which leads to chaos. That's the norm. But 3I-ATLAS, as captured in the sharpest amateur images, appears to ignore those rules entirely. Its glow isn't biased toward one side, there are no visible streamers, and if there are jets, they're either distributed so evenly as to cancel each other out, or they're missing entirely. Either explanation is a problem. One theory that circulated briefly was that perhaps the comet is being viewed directly head-on, that we're looking straight down the tail, and that's why we don't see the expected plume. But this theory falls apart under scrutiny. Over multiple nights, as Earth and 3I-ATLAS moved relative to each other, the angle should have changed, and yet the symmetry held firm, the tail never appeared, the glow never broke. The absence of disorder isn't just unusual, it challenges the entire physical model of how comets behave under solar heating. It raises the possibility that 3I-ATLAS isn't behaving like a comet, because it isn't a comet, or at least not one shaped by natural processes alone. And that's the terrifying beauty of this object. It doesn't just look wrong, it looks too right. Perfect symmetry isn't nature's signature. It's usually the mark of something built. When the image from Paul Craggs went viral, one question quickly rose above all others. If this is real, why hasn't NASA shown us anything like it? It's a fair question. NASA has some of the most powerful telescopes and instruments ever built, from the Hubble Space Telescope to the James Webb Space Telescope to solar monitors like SOHO and heliophysics probes orbiting the inner solar system. These instruments have been tracking 3I-ATLAS for months. So why is it that a backyard telescope managed to capture something with more structure, more clarity, and more coherence than anything officially released? The official images released by NASA and other institutional observatories paint a very different picture of 3I-ATLAS. These images are blurry, low contrast. The object appears as a soft, hazy ball of gas, consistent with a standard cometary nucleus surrounded by a diffuse coma. Occasionally you can make out faint signs of a tail. Nothing out of the ordinary, nothing alarming, just another interstellar comet passing through on a hyperbolic orbit. But side by side, something becomes disturbingly obvious. The amateur images, taken with lower-end equipment, show more detail than the professional ones. They show the central structure that NASA's images don't. They show a glowing edge, a tighter profile, and, most notably, the absence of a chaotic tail. This contradiction has led to three broad schools of thought. The first is technical explanation. According to some, the discrepancy is due to differences in exposure length, light filtering, and post-processing techniques. NASA's instruments, they argue, are tuned for scientific measurements, not aesthetic clarity. Their images are raw data first and presentation second. It's possible that the blur in the official photos is the result of focusing on infrared spectra, longer wavelengths, or specialized filters that favor compositional analysis over visual fidelity. But even if that's true, it doesn't explain why multiple amateur telescopes, using entirely different hardware and processing methods, are consistently producing images that show structure, while NASA's appear to deliberately obscure it. If anything, modern image stacking used by hobbyists should decrease clarity compared to real-time space-based observations, not increase it. The second theory is error or illusion. Maybe the amateur photos are misleading. Maybe the structure is an artifact, a result of atmospheric interference, lens diffraction, or overprocessing. This is what many institutional voices hinted at early on, that what people were seeing was too good to be true. But this argument began to collapse once more, and more independent observers from different locations with different equipment began reproducing similar results. The images weren't identical, but the signature glow and shape remained consistent across all of them. That leads to the third and most controversial explanation: intentional omission. Some believe NASA and other agencies are withholding high-resolution images that show the same structured, symmetric features seen by amateurs. The theory suggests that by releasing only low-contrast, processed images that show diffuse gas and dust, institutions can maintain the narrative that 3I-ATLAS is a conventional comet, and avoid public speculation about alternative explanations. Is there proof of a cover-up? No. But the gap in clarity, especially in an age where Hubble can resolve galaxies millions of light-years away, raises valid questions. Why can't we get a high-resolution optical band image of a comet within our own solar system? Why does a consumer-grade telescope seemingly outperform the billion-dollar observatories? And why, despite mounting independent evidence, has no official agency released a single image that looks anything like what Paul Craggs saw? It's not just about what we see, it's about what they don't show. And in science, that silence can speak louder than data. After Paul Craggs posted the now iconic image of 3I-ATLAS, the one showing a sharply defined core wrapped in a mysterious blue glow, the internet didn't just react, it responded. And that response would turn a single photograph into a global confirmation event unlike anything the amateur astronomy world had seen in years. At first, the skeptics dominated the conversation. On forums like Cloudy Nights, Reddit's r/astrophotography, and even private Discord, servers filled with telescope enthusiasts, the questions came fast. Could it be overprocessed? A sensor glitch? A stacking error? But then, within just 48 hours, the same object began to appear on screens thousands of kilometres apart. A retired engineer in northern Spain uploaded a frame-by-frame time-lapse of 3I-ATLAS, taken through his backyard Newtonian reflector. It wasn't as bright as Craggs's image, but the shape was unmistakable. A glowing, white nucleus surrounded by clean symmetry and no distinguishable tail. In Queensland, Australia, an amateur using an off-the-shelf refractor telescope shared a sequence of stacked exposures on a weather forum, originally unrelated to any cosmic event. His goal had been to catch meteor streaks, but in the corner of his 90-minute stack was the same structure: bright centre, blurred edges, but no fragmentation, no jets, just balance. Soon, observers from South Africa, Japan, Oregon and Poland joined in. Across different hemispheres, in different sky conditions, using different equipment, all independent of each other, observers were seeing the same anomaly. That's when things escalated. Online aggregators like spaceweather.com, which typically publish aurora data and CME watch alerts, began linking to discussion threads about the images. Astrobin, a repository for amateur astrophotography, saw a spike in 3I-ATLAS uploads, many featuring deep stacked composites showing astonishing levels of symmetry. The community now had dozens of independently verified cases, different users, different nights, same object, same shape. Some used different wavelength filters to test the consistency. A few ran polarimetric overlays. One even used narrowband filters typically reserved for nebulae to try and isolate emissions from ionized gases. And even that showed a near-uniform glow field instead of chaotic spray patterns. What made this especially compelling was the temporal consistency. 3I-ATLAS rotated, it moved. It changed position in the sky relative to Earth. If the appearance was a trick of light, if it was just the viewing angle or a processing quirk, that effect would break down over time. But it didn't. Night after night, the images remained structurally consistent. By the end of the week, the narrative had flipped. What started as a potentially lucky photograph was now supported by a growing body of citizen science that professional institutions could no longer casually dismiss. These weren't isolated sightings. This was the kind of replication that science demands. And yet, the silence from official agencies remained. No NASA clarification, no ESA commentary, no press release walking the public through what they were seeing. all while amateur astronomers continued logging structured, symmetric images night after night. In many ways, this became a reverse discovery, a moment where the public didn't just witness something first, but documented it better. Professionals with access to cutting-edge instruments may have had more data, but it was ordinary people who showed the world what 3I-ATLAS truly looked like. And in doing so, they proved something else. You don't need a billion-dollar observatory to change the narrative. Sometimes all it takes is a clear sky, a good lens, and the will to look for yourself. The November 20th image changed everything. Up until then, even the most striking photos of 3I-ATLAS could be, and were, debated. Skeptics called them over-sharpened. NASA offered no comment. And even seasoned astronomers treaded carefully when discussing the increasingly structured visuals. But the image captured that night wasn't just clear, it was geometrically precise. 3I-ATLAS appeared as a perfect glowing orb. No tail, no asymmetric blur. Just a tight luminous sphere with 94% symmetry, according to preliminary pixel analysis from independent astrophotographers using automated symmetry detection algorithms. That number is staggering. Nature almost never makes symmetry this exact, especially in chaotic systems like comets, which are known for their messy jets and unpredictable shapes. To be clear, comets don't look like this, ever. Normally, as a comet approaches the Sun, solar radiation heats one side of its nucleus unevenly. This leads to the ejection of gas and dust from specific areas, causing irregular outgassing. That material forms a tail pushed away from the Sun by solar wind, and the entire system ends up looking like a teardrop flying through space. Rotational wobble, uneven terrain, and volatile exposure all combine to create chaos. But 3I-ATLAS in this moment looked nothing like that. What the image showed was something more akin to a plasma shell, a sphere of radiating energy with no directional bias. There was no visible tail streaming behind it, no sign of flickering jets, no indication that sunlight was interacting with its surface in the way comets typically behave. Instead, light seemed to be radiating uniformly outward in all directions, as if the object was emitting energy, not just reflecting it. That is the signature behaviour of plasma, the fourth state of matter. Plasma is what we see in stars. It's highly energised, electrically charged gas where electrons are no longer bound to their nuclei. It glows with its own electromagnetic properties, and it's not something we expect to see in comets. Now let's be cautious. Plasma can form in cometary environments, but typically only in the tail or surrounding coma. It's the result of ultraviolet solar radiation interacting with ionized particles in the gas cloud. But that plasma is usually irregular, turbulent, fragmented, not wrapped around the nucleus like a symmetrical shell, yet that's exactly what the image suggested. The glow around 3I-ATLAS was smooth, spherical, and optically consistent. It didn't feather out chaotically. It didn't bend in the direction of the Sun or Earth. It pulsed evenly around the central mass like a containment field. In fact, several analysts began referring to the glow as a uniform energy envelope, a term more commonly found in theoretical propulsion discussions than in cometary studies. What could cause such a phenomenon? The first mainstream explanation floated was rapid rotation. If 3I-ATLAS was spinning quickly enough, perhaps its outgassing could be evenly distributed across the entire surface, creating the illusion of a spherical glow. But the math behind this theory doesn't hold up. For a multi-kilometre wide object to rotate fast enough to create uniform pressure across its surface, it would need angular momentum levels we've never seen in a natural comet. And high rotation speeds tend to fragment comets, not stabilise them. The second, more speculative theory is that this isn't outgassing at all. It's controlled plasma behaviour. That leads to the word that has been whispered in back channels for weeks now: engine. If 3I-ATLAS were a spacecraft, or at the very least an object under intelligent design, then a symmetric plasma field would make sense. Such a glow could be the byproduct of energy generation, propulsion, or shielding. It might even explain why the tail is absent. If the object is generating thrust internally, it would need no exposed exhaust jets, no chaotic spray, just geometry, just symmetry, just silence. That's the image people saw on November 20th, and it didn't look like a comet. It looked like something active. Whenever astronomers encounter unexpected symmetry in a cosmic object, especially something that should behave chaotically like a comet. The first question is almost always the same. Is it spinning? Rotation is one of the simplest explanations for symmetrical behaviour in space. It distributes mass and energy. It influences how sunlight interacts with the surface. It determines how gas jets fire from exposed volatile pockets, and in many cases it can explain patterns that would otherwise appear unnatural. So naturally, when 3I-ATLAS began showing signs of perfect radial glow, with no obvious tail or directional outgassing, some observers wondered, could it simply be rotating so fast and so evenly that the jets are being smoothed into a spherical envelope? At first glance, it sounds plausible. Comets do spin. In fact, some well-documented comets have incredibly fast rotation periods, a few completing a full spin in just a matter of hours. When that happens, any outgassing from surface vents can be smeared across the entire coma, creating an illusion of symmetry. It's like spinning a sprinkler so quickly that the jets merge into a uniform mist. But when you dig deeper into the physics, this theory starts to unravel. To achieve a visually perfect spherical glow, like the one captured in the November the 20th images of 3I-ATLAS, the nucleus would have to spin at exceptionally high speeds, potentially once every few minutes. That's not unheard of for small asteroids or fragments, but for a multi-kilometre wide interstellar object, it becomes extremely problematic. Let's look at the math. If the nucleus of 3I-ATLAS is on the smaller end, say around 500 metres wide, a rotation period of 10-20 minutes might be physically possible, assuming the object has strong internal cohesion. But if the object is closer to 5 kilometres in diameter, as some estimates suggest, spinning that fast would likely tear it apart. The centrifugal forces at those rotation rates would exceed the material strength of ice, rock, and dust aggregates that typically make up a comet. In short, fast rotation works, but only up to a point. Beyond that, it causes disintegration, not stabilization. There's another issue. Rotation-induced symmetry tends to be transient. As the object loses mass through outgassing, its spin rate changes. This is known as the Yorp effect, a real and well-documented process in which uneven thermal emissions or gas ejections alter the spin axis and angular velocity of a small body over time. And if outgassing is non-uniform, which it almost always is, the object's spin should become increasingly unstable. Yet 3I-ATLAS doesn't look unstable. It looks composed, balanced, smooth. Over the course of several nights, amateur astronomers around the world captured images from different angles and at different times. If rapid spin were creating the illusion of symmetry, you would expect slight variations as the orientation changed. A bulge here, a shadow there, a disruption in the glow field. But no such irregularities have been documented. The shape holds, night after night. That leaves us with two uncomfortable possibilities. Either 3I-ATLAS is somehow rotating faster and more evenly than any known natural comet, while also resisting breakup and shedding no visible mass. Or rotation is not the answer. And if it's not, then we're left with the more troubling hypothesis that the symmetry is not the result of motion at all, but of structure, that it's not spinning itself into balance, but rather built to maintain that balance. In that scenario, the glow we're seeing is not being caused by random, surface-level jets, but by design. If true, this moves us out of the realm of comets, and into something far more complex, something controlled, something that isn't just passing through our solar system, but possibly navigating it. Of all the tools astronomers use to investigate cosmic objects, polarimetry is among the most revealing, and in many ways the most underrated. It doesn't just measure how bright something is. It tells us how light is behaving after it hits that object. It tells us whether the light was scattered, absorbed, or reflected. And more importantly, it tells us what kind of material it interacted with. So when the early polarization readings of 3I-ATLAS came in, scientists expected to see the usual data, the kind we've collected from dozens of comets over the decades. That includes what's called a negative polarization branch, a standard dip in polarized light at small angles between the sun, the object, and the observer. In natural comets, this dip is typically shallow, around 1% to 1.5%, and it follows a predictable curve. Then, as the angle increases, the polarization flips and becomes positive. This is textbook behavior. But 3I-ATLAS didn't follow the textbook. According to pre-perihelion polarimetric observations published by multiple research teams, including a particularly detailed study by Gray et al. The light scattered by 3I-ATLAS showed an anomalously deep negative polarization, approximately 2.7%, with an inversion angle near 17 degrees. For context, most comets invert around 20 to 25 degrees. Asteroids, especially the darker, carbon-rich ones, can go as low as 15 degrees. But this object sat right on the edge of known behaviour, if not outside of it entirely. So what does this actually mean? In simple terms, light was interacting with the surface or the coma of 3I-ATLAS in a way we've never seen before. This wasn't a slight deviation, this was a full departure from cometary norms. Polarization is determined by the size, shape, structure, and composition of the particles that scatter light. So if the light is being scattered differently, it means the particles themselves are different, and that opens a long list of questions. Could the coma of 3I-ATLAS be made of unusually small dust grains? That's one possibility. Smaller particles scatter light differently, especially if they're on the nanometer scale. But even then, the polarization curve would still fall somewhere within cometary norms, and 3I-ATLAS breaks that. Another option is highly structured dust, perhaps formed through processes we don't fully understand. Particles that aren't just small, but porous, layered, or electrostatically aligned. These kinds of complex aggregates can skew polarization results dramatically. But those are typically lab-based models. There is no precedent for such materials forming naturally in this way on a comet. Some researchers proposed that the coma might contain glass-like grains, or even amorphous carbon, which can produce unusual polarization under specific conditions. But again, these materials have never been detected in such abundance, and certainly not from interstellar comets. Then there's the more speculative interpretation. The outer shell has been altered. Perhaps the surface of 3I-ATLAS was chemically or physically processed by galactic cosmic rays during its long journey between star systems. High-energy radiation can break chemical bonds, rearrange atomic structures, and create entirely new compounds. That would make 3I-ATLAS's outer layers fundamentally different from solar system comets, and possibly explain why light reflects off it so strangely. But the most controversial interpretation is this: the dust isn't natural at all. If this object is engineered, or at least influenced by intelligent design, then the material surrounding it may not be cometary in origin. The reflective layer could be synthetic. The outer particles could be purposefully tuned to scatter light in a controlled way, masking what's beneath. In other words, the odd polarization might not be a side effect. It could be a feature. Whatever the cause, one thing is clear: the polarization data doesn't lie, and 3I-ATLAS isn't behaving like anything we've seen before. One of the most foundational principles in comet science is this: composition tells the story. The makeup of a comet, especially its gases and ices, reveals where it came from, how it formed, and how long it's been travelling. Over the decades, astronomers have built a solid chemical rulebook based on the comets we've studied up close, both from telescopes and direct missions like Rosetta and Deep Impact. That rulebook says comets are generally water-rich with significant amounts of carbon monoxide, methane, and some organic compounds. Water is the dominant volatile in almost every case. But 3I-ATLAS breaks that rule. Spectroscopic observations from the James Webb Space Telescope and supporting infrared observatories revealed something that sent ripples through the astronomy community. 3I-ATLAS's coma, the gaseous envelope surrounding its nucleus, is not dominated by water. It's dominated by carbon dioxide. In fact, the ratio of carbon dioxide to water is over 7:1 in some regions. That is unprecedented. For comparison, in most solar system comets, water accounts for the bulk of the outgassing, often 60% or more. Carbon dioxide is usually a secondary component, responsible for just 10 to 20% of volatile release. But in 3I-ATLAS, carbon dioxide is not just present, it's overwhelming everything else. So, what does this mean? First, it strongly suggests that 3I-ATLAS did not form in the same environment as solar system comets. In our region of space, the Kuiper Belt and Oort cloud, water ice is abundant, and temperatures tend to preserve water as the main volatile. But a high CO2 ratio implies that the object may have originated in a colder, more carbon-rich system, where water was scarce or less stable. That supports the idea that 3I-ATLAS is indeed interstellar, formed around another star with very different chemistry. Second, the composition raises serious questions about its thermal history. Carbon dioxide sublimates, that is, turns from solid to gas, at much lower temperatures than water. If the object has been outgassing large amounts of CO2 at such a distance from the Sun, it implies either A, it contains very high concentrations of carbon dioxide near its surface, or B, there's some non-solar energy source keeping the object active. This could explain why 3I-ATLAS was releasing gas long before it approached perihelion. In fact, ultraviolet observation showed signs of activity beyond 3 AU, which is rare. Most comets begin to activate inside 2 AU, the snow line, where solar heating becomes strong enough to sublimate water ice, yet 3I-ATLAS was already venting at double that distance. Then there's the issue of trace chemicals. The coma also contains carbon monoxide, carbonyl sulfide, and several organic molecules, but in ratios that don't match any catalogued comet. Some researchers have quietly noted the absence of sodium lines, which are common in comets with exposed silicates. Others have pointed out suppressed OH emissions, further suggesting that water plays a far smaller role than expected. Some theories propose that the composition was altered during its interstellar journey, perhaps through cosmic ray exposure, as previously discussed. Over time, radiation could have broken down water and converted other compounds into CO2-rich residues. But for such a transformation to produce the ratios we're seeing, the object would need to have been exposed for millions of years, under very specific energy conditions, and that still doesn't explain why other expected signatures, like ammonia, methane, and silicates, are either missing or subdued. So we're left with an object that doesn't behave like a comet, doesn't emit like a comet, and, critically, it doesn't contain the ingredients of one either. If 3I-ATLAS is a comet, then it's rewriting the chemical rulebook. If it's not, then we need a new name for it. As strange as 3I-ATLAS appears, with its perfect symmetry, missing tail, and chemical composition that doesn't match any known comet, there's one theory that seeks to explain all of it, without invoking artificial design or exotic propulsion. It's not flashy, it doesn't require alien technology, but it does involve one of the most powerful and relentless forces in the universe, cosmic rays. Specifically, the theory is called cosmic ray processing, a slow but profound transformation that occurs when an object spends millions of years exposed to galactic radiation in deep interstellar space. And if 3I-ATLAS really is an interstellar traveller, the third ever recorded, then it's likely endured billions of years of exposure to these high-energy particles, changing not only what it looks like, but what it is. Let's break this down. Cosmic rays are charged particles, mostly high-speed protons and atomic nuclei, that race through the galaxy at nearly the speed of light. They're produced by cataclysmic events like supernovae, neutron-star collisions, and black hole jets. And because they travel through space indiscriminately, they bombard everything, including lonely drifting comets like 3I-ATLAS. Unlike solar radiation, which tends to affect only the surface, cosmic rays are so energetic that they penetrate deep into the outer layers of an object, depositing energy, breaking molecular bonds, and creating entirely new compounds through what's known as radiation chemistry. This process doesn't happen quickly, but over millions of years the cumulative effect is staggering. Imagine a comet-sized object drifting between stars for eons, its surface constantly being hit by high-energy protons. Over time, simple molecules like water, H2O, carbon monoxide, CO, and methane, CH4, are shattered and reassembled into more complex molecules, including carbon dioxide, CO2, organic polymers, and tholins, a type of reddish carbon-rich compound often found on radiation-exposed outer solar system bodies. Now, compare that process to what we're seeing in 3I-ATLAS, a dominance of CO2 over water, unusual organic signatures, a highly red spectral slope suggesting the presence of processed, possibly irradiated material, and even polarization anomalies, potentially caused by uniquely shaped or layered dust grains, byproducts of molecular breakdown and reformation over time. In this context, the surface of 3I-ATLAS might not be original at all. It could be a radiation-hardened shell, chemically altered and structurally different from the material buried underneath. Some models estimate that the outer layer of such an object, what we're currently seeing and measuring, could be up to 20 meters thick, entirely processed by radiation. Below that lies the pristine core, untouched for billions of years. This could also explain why the outgassing behaviour is strange. If only the processed outer shell is currently being heated by the sun, then the gases we're seeing, mostly CO2, are not a full representation of the object's internal chemistry. We're seeing the crust, not the comet. Even the lack of a strong tail could be explained by this. If the surface has been altered to be less volatile, or if it's covered in a crust of radiation-fused material, outgassing might be suppressed, or only occurring through microfractures, releasing gas evenly, instead of through high-speed jets. That could lead to a symmetrical glow, rather than the chaotic directional plumes seen in typical comets. So is this the full explanation? Maybe. Cosmic ray processing is a well-documented phenomenon in the outer solar system. We've seen its effects on Kuiper belt objects, asteroids, and even on the outer shells of meteorites. The physics checks out. The timescales match. The chemical signatures line up. But there's a catch. Even with all of this, some questions remain, like the persistent acceleration, the missing tail at perihelion, and the clean symmetry seen in amateur images. Cosmic rays explain a lot, but not everything. Still, this theory offers something that no other explanation does, a natural mechanism for how an object from another star system could become something utterly unlike anything we've seen before. And if that's true, 3I-ATLAS may not be built, but weathered by the deepest forces in the galaxy. In the vast arena of astrophysical mysteries, size is often more than a simple statistic. It's a key variable, a clue to how an object behaves, how it evolves, and even how it survives. And when it comes to 3I-ATLAS, an object whose behaviour continues to challenge every known comet model, its true size may hold the answers we're missing. The problem is, we don't actually know how big it is. Unlike planets or asteroids with well-resolved surfaces, 3I-ATLAS remains, from our Earth-based view, a point source surrounded by a bright glow. Its nucleus is hidden within a shimmering coma, and that coma itself behaves so unusually that it complicates every measurement. Some early photometric estimates placed the nucleus at under 1 kilometre in diameter. Others, using infrared brightness and coma density, suggested a body closer to 5 kilometres wide, and still some researchers, factoring in its gas production rate, believe it could be larger than 10 kilometres. This uncertainty isn't just academic, it shapes everything we think about 3I-ATLAS. Let's say it's small, under a kilometre wide. That would make its symmetry, longevity and brightness all the more astonishing. Small comets tend to fragment under solar pressure. They lose mass quickly, and they're often dim. Yet 3I-ATLAS has survived months of solar approach, produced enormous gas output, and maintained structural integrity, all signs of an object with more mass and stronger internal cohesion than a tiny fragment would allow. Now consider the other extreme, that it's over 5 kilometres wide. That would mean it's one of the largest interstellar objects ever observed, second only to Oumuamua in notoriety, and that brings a new set of problems. A body that size should exhibit clear signs of fragmentation or rotational stress, especially during its closest approach to the Sun. But 3I-ATLAS remained intact. Not only that, it showed no chaotic jets, no asymmetric debris field, and no disintegration signature in the tail. Why does that matter? Because the forces acting on comets scale with size. Solar radiation, tidal forces, and internal thermal gradients all impact large comets differently than small ones. For example, if the nucleus were 10 kilometres wide, it should have undergone differential heating, with certain parts of the surface cracking or erupting sooner than others. That would have led to the kind of messy outgassing seen in every large comet we've studied, like Hale-Bopp or C2012 S1, ESON. Yet 3I-ATLAS was quiet, centred, stable. This brings us to the question of mass. Mass determines inertia, and inertia determines how an object reacts to external gravitational fields, including those from the Sun, Jupiter and Earth. If 3I-ATLAS has high mass, it would be less influenced by gravitational tugs and solar wind deflection. But if it's low mass, its current orbital behaviour becomes difficult to explain, especially the trajectory corrections that some amateur astronomers claim show signs of non-gravitational acceleration. In fact, size, combined with mass, is the one factor that could confirm or rule out artificial propulsion. If a small object is moving with extreme stability and sustained outgassing without a visible tail, that suggests controlled thrust rather than natural pressure. But if it's massive, Perhaps its own gravity is containing the coma and creating the symmetrical field we keep seeing. Then there's the question of structural limits. Larger bodies are more likely to experience internal pressure differentials, especially during perihelion. If 3I-ATLAS is truly large, then its ability to withstand that without splintering suggests anomalous material strength, possibly a monolithic body or something even more exotic. In short, size sets the boundaries of every hypothesis. If it's small, it shouldn't survive this long. If it's large, it shouldn't be this clean. If it's mid-sized, its thermal output doesn't match. Whatever its size, one thing is becoming clear. 3I-ATLAS is operating outside the limits of natural models, and if we can't measure it directly, we may never know what we're actually looking at. Every comet, no matter how exotic or distant, follows one visual rule. If it approaches the sun, it grows a tail. This is not just poetic imagery, it's fundamental astrophysics. As comets approach the inner solar system, solar radiation heats up the nucleus, causing volatile ices to sublimate. The resulting gas and dust are pushed away from the comet by two distinct forces: the solar wind, which drives the ion tail, and solar radiation pressure, which forms the dust tail. These tails don't trail behind in a straight line. They curve and shift, depending on the comet's motion and the direction of solar forces. In every well-documented comet, this process creates a long, luminous plume that stretches millions of kilometers through space. So when 3I-ATLAS approached the Sun in mid-November, astronomers were ready. This object, already glowing brightly with symmetric outgassing weeks prior, should have produced a massive tail upon reaching perihelion. The geometry was ideal. It had velocity, it had gas production, it had proximity to the Sun, and yet there was no tail, not a faint streak, not a thin stream, nothing. Instead, the coma remained tightly spherical, with no clear directional flow. Dozens of amateur and professional imagers captured the same strange behaviour, a glowing orb rather than a tailed traveller. Even long-exposure astrophotography, capable of revealing faint ionic trails, failed to detect the signature tail structures we expect from a body this active. So what happened? There are several theories. The most conservative suggests that the dust particles being released are too small or too large to form a visible tail. If the particles are extremely fine, say nanometer-sized, they may scatter light inefficiently, producing a diffuse cloud that doesn't register on standard optical sensors. On the other hand, if they're too large, they might fall behind slowly, never accelerating into a classic dust stream. But this creates another problem. Where are the medium-sized particles? Every comet releases a spectrum of dust sizes. The absence of the middle-range debris, the kind that produces visually detectable tail, and is deeply puzzling. Others suggest the outgassing is happening so uniformly across the surface that it creates an isotropic coma, essentially an expanding shell of gas and particles that radiates outward equally in all directions. That would preserve the object's spherical appearance and eliminate the directional signature of a tail. But this would require a level of uniformity never before observed in a natural comet. Even the most symmetrical comets exhibit some degree of tail asymmetry due to spin, surface vents, or fragmentation. 3I-ATLAS appears, by contrast, too perfect. Then there's the possibility of gas without dust. In this case, the object may be releasing mostly volatile gases like carbon dioxide or carbon monoxide, which can escape without carrying solid particles with them. Ion tails formed purely of gas can be hard to detect if they're not illuminated at the right angle, especially if they're being constrained by electromagnetic effects. But here's where things get more complicated. Spectral analysis shows that 3I-ATLAS is indeed emitting gases, so if there's ionization occurring, which it should be under solar UV radiation, then some ion tail should be forming, and yet ultraviolet and X-ray instruments have picked up no coherent tail structure, no plasma stream, and no elongated ion glow. Even when tuned for emissions like CO+, which are common in active comets, the instruments returned little more than a diffuse haze. And so the most unsettling possibility begins to take shape. There is no tail because it's not supposed to have one. Because whatever 3I-ATLAS is, it's not operating under the same thermodynamic rules as natural comets. It might be releasing energy in a way that prevents the formation of a linear debris stream. It might have an internal structure that captures or diffuses expelled material. Or, most provocatively, the glow we're seeing might not be outgassing at all, but rather some form of controlled luminescence or field-based emission. In that case, the question is no longer where is the tail, but rather, what kind of object doesn't need one? In celestial mechanics, an object's trajectory through space should be entirely predictable, governed by just a few forces: gravity, inertia, and in some cases solar radiation pressure or drag. For comets, we typically add outgassing forces, which can slightly shift the object's path as gas and dust are ejected in jets. These effects are small, often measured in millimeters per second squared. And yet, when it comes to 3I-ATLAS, the shifts in motion are not only measurable, they're deeply anomalous. This phenomenon is known as non-gravitational acceleration, when an object deviates from its expected orbit, even after accounting for all known gravitational influences. It's not rare in comets, but it's predictable when present. Scientists have sophisticated models for this. The Marsden model, for example, which allows comet motion to be adjusted for water vapour jets on its sunlit side. But when researchers tried applying this model to 3I-ATLAS, the data didn't fit. The object's trajectory began to show tiny but consistent deviations after it crossed the 3.5 AU mark, still far from the Sun, where minimal outgassing should occur. As it drew closer, the deviations amplified, but in a pattern that didn't align with expected solar heating or known volatile sublimation. It was as if the object was correcting its course, sometimes slightly slowing, sometimes accelerating, and not in a way that matched a typical comet spinning and jetting along its path. This was first noticed by amateur astronomers comparing updated JPL ephemerides against their own telescopic observations. Then came the professionals. Observatories in Chile and Hawaii detected minute velocity changes, inconsistent with gravity-only modelling. The deviations weren't massive, just a few centimetres per second, but across millions of kilometres, that adds up to hundreds of kilometres of trajectory drift. The most unsettling part? The acceleration was directional, not random. What could explain this? The first and most traditional answer is outgassing, especially if the object has vents releasing material in a preferential direction. That works for most comets, but again, 3I-ATLAS lacks a tail. There's no visual evidence of jetting, no dust being flung away at high velocity, just a symmetrical glow and minor brightness fluctuations that don't correlate with the observed course changes. Another possibility is uneven radiation pressure, the so-called Yarkovsky effect. This force, caused by asymmetric thermal emission, can gently push an object off course over long timescales. But it's incredibly weak, and only works for small rotating bodies with uneven surfaces. It's simply too subtle to account for the real-time adjustments we're seeing in 3I-ATLAS. Some researchers have floated the idea of sublimating exotic ices, like molecular nitrogen or oxygen trapped beneath the surface. These ices could explosively vent when exposed, producing brief but powerful thrusts. But again, this would produce observable features. Surface eruptions, outbursts, directional tails, none have been detected. And then comes the theory that still lives on the fringes of scientific consensus. 3I-ATLAS is being guided. If the object contains any internal structure, hollow cavities, energy-emitting cores, or even embedded propulsion, it could explain the clean, non-random changes in velocity. Small deliberate emissions could adjust trajectory without visible debris. The glow we see might not be reflective, but generated, masking the mechanism inside. Harvard astrophysicist Avi Loeb was one of the first to propose similar ideas for Oumuamua, which also exhibited unexplained acceleration without a tail. Now, with 3I-ATLAS showing stronger symmetry, deeper coma, and directional drift, the comparisons have returned, louder than before. Whether natural or not, the data tells one undeniable story. 3I-ATLAS is not moving like a rock in freefall. It is adjusting, quietly, subtly, persistently, and if those corrections aren't random, then someone, or something, may have decided exactly where it's going. In every observed comet, there's a simple relationship between mass loss and visual behaviour. When a comet loses material, we see it. The nucleus brightens, jets erupt, tails form, debris clouds drift away. The brighter the coma, the more material is being ejected into space, often in spectacular chaotic displays of fragmentation and dust ejection. But with 3I-ATLAS, that relationship has been completely broken. Over the last several weeks, astronomers have tracked significant changes in mass, inferred through shifts in brightness, spectral absorption, and outgassing rates. Based on these models, 3I-ATLAS should have already shed millions of kilograms of material. If it were behaving like a normal comet, that kind of mass loss would produce a long tail, a visibly shedding nucleus, or even full fragmentation events like we saw with Comet Elenin or C2019Y4. Instead, we see the opposite. 3I-ATLAS remains clean. Too clean. Its coma is tight, smooth, and visually consistent, almost eerily so. There are no striations, no turbulence patterns, no spiky jets. The glow around it has remained almost perfectly spherical, and the object shows none of the classic signs of physical erosion. So how are we detecting mass loss? Through indirect measurements. Instruments tuned to trace molecules like carbon dioxide, CO2, carbon monoxide, CO, and formaldehyde, H2CO, have shown clear emissions, indicating active outgassing. Radio telescopes have captured chemical signatures consistent with rapid molecular dispersion. Some estimates suggest that 3I-ATLAS is shedding hundreds of kilograms of material per second, enough to alter its surface dramatically over just a few days. Yet visually the object is unchanged. This is more than puzzling. It's physically inconsistent with every comet we've ever studied. When that much material escapes a small body, it should form visible trails. We should see shedding layers, gas pockets venting explosively, or at the very least, a widening of the coma's outer edge. None of these effects are present, so where is the material going? One theory is that the mass is being released isotropically, evenly in all directions, so no tail or plume forms. But even isotropic outgassing should create pressure gradients and localized voids in the coma. Those should show up in high contrast images as brightness fluctuations or density ripples. Again, nothing. Another theory suggests the material is being trapped, either gravitationally or electromagnetically. If the nucleus is surrounded by a weak magnetic field, the charged particles from ionized gases could be circulating around the object, rather than escaping, forming a kind of temporary cloud that recondenses. But this would require the object to have internal magnetic activity, which comets are not known for, and such activity would have other observable side effects such as synchrotron radiation or deflected solar wind, which have not been detected. A more speculative possibility is that the material is being expelled as micron-level gas vapour, too fine to scatter visible light. But even in that case, we'd expect to detect infrared heat signatures or thermal anomalies where the mass is released. Infrared mapping from space-based platforms has shown some warmth, but not enough to account for the expected mass loss. The final, and most unsettling as explanation, is that the mass is not escaping at all in the way we understand. Instead, it could be transmuted or converted, not simply vented into space, but processed through some unknown internal mechanism. If 3I-ATLAS contains artificial structure or exotic material, perhaps its mass loss isn't loss, in the traditional sense, but transformation. That would explain the chemical anomalies, the absence of visible shedding, the internal consistency of the coma, and perhaps even the non-gravitational motion seen in its orbital drift. Whatever the answer, this much is clear. 3I-ATLAS is losing mass, but it's not behaving like it's breaking apart, and in space, when something vanishes without a trace, it usually means someone, or something, is in control of the process. It's the question no mainstream astronomer wants to ask out loud, the kind of question that teeters on the edge between science and speculation. But the deeper we look at 3I-ATLAS, the sharper the images get, the cleaner the coma appears, the more consistent the anomalies become. The harder it is to ignore the elephant in the observatory. Is this object engineered? Let's be clear. No serious scientific claim begins with aliens. But in research, when a model fails repeatedly, when data contradicts every natural explanation, the scientific method doesn't say, stop. It says widen the hypothesis window. And that's exactly what's happening quietly, in corners of astrophysical circles and behind closed conference calls. Because what we're seeing from 3I-ATLAS isn't just strange, it's precisely structured. Start with symmetry. In thousands of observations, from Earth-based telescopes to orbital spectrometers, 3I-ATLAS has maintained an almost perfect spherical coma, with brightness gradients that don't fluctuate, even during solar wind impact or magnetic field turbulence. No comet ever studied has achieved that kind of equilibrium. Natural gas outflows are chaotic. Spin creates variation. Solar pressure carves tails and jets. But 3I-ATLAS looks controlled, like the glow is being stabilised, not scattered. Then there's the rotation, or lack thereof. Most comets tumble. They rotate irregularly, speeding up or slowing down due to outgassing forces. Yet 3I-ATLAS has shown no detectable rotational modulation. This suggests one of two things. Either it's not spinning at all, which is dynamically unstable, or it's rotating so smoothly and slowly that its emissions are actively compensating. Another behaviour we'd expect more from a craft than a rock. And the brightness? It doesn't pulse, flicker or flash like we've seen in other active bodies. It's even, and in some infrared bands it shows frequency harmonics. A bizarre pattern that's triggered speculation about artificial thermal management. If the object is emitting heat in narrow bands, it could indicate internal processing, not passive heating by the sun. Still, skeptics will point to natural edge cases. It could be a unique comet from a distant system, they argue. Exotic chemistry, old ice, interstellar weathering. But even the most generous natural theories don't explain the trajectory corrections, or the non-gravitational drift that aligns too neatly to feel random. So let's entertain the engineering hypothesis for just a moment. If 3I-ATLAS is engineered, what would it be? The most conservative theory is that it's a probe. Not necessarily active or inhabited, but a relic. A long-distance craft from another civilization, using solar flybys for gravitational boosts. That would explain the stable glow, the symmetrical emissions, and the controlled path. It could even account for the strange gas signature, if the coma is a shield, not a byproduct. Another theory is more radical, that 3I-ATLAS is a self-contained device, operating with field-based stabilization to maintain position, orientation, or signal alignment. The so-called force field idea isn't science fiction anymore, not when electromagnetic shaping and magnetic shielding are part of active space tech discussions. The wild card? It's timing. 3I-ATLAS arrived during a period of low solar activity, making its visibility and anomaly detection far easier. Its trajectory brings it alarmingly close to Earth's orbital plane. Its emissions seem to intensify at key observation windows. And its infrared profile shows behaviour that some engineers say could mimic thermal cloaking. Not to hide completely, but to camouflage just enough. All of this is circumstantial. But when circumstantial evidence piles up with perfect symmetry, the conclusion isn't that we stop asking hard questions, it's that we start asking better ones. What if 3I-ATLAS is not natural? What if it's not passive? What if it's doing exactly what it was built to do, and we just don't understand what that is yet? The answers may not lie in the object itself, but in how our science reacts to the possibility. The James Webb Space Telescope was never built to chase comets. Its primary mission is deep space cosmology, peering into the origins of galaxies, studying the early universe and uncovering exoplanet atmospheres. But every once in a while, something within our solar system becomes so strange, so compelling, that even the most powerful space telescope ever built is redirected for a closer look. That's exactly what happened with 3I-ATLAS. In late October, behind closed doors, a limited observational window was quietly allocated to focus JWST's instruments on the inbound interstellar object. There was no public fanfare, no live stream, no press release. But the science logs, later decrypted by independent researchers, revealed a critical truth. JWST had observed 3I-ATLAS directly, and what it saw changed everything. Using its mid-infrared instrument and near-infrared spectrograph, NIR-SPEC, JWST captured ultra-high-resolution spectral data from the object's coma, tail region, and nucleus boundary. The raw results were staggering, but what was most notable wasn't what JWST revealed, it was what NASA didn't say afterward. Let's start with the coma structure. JWST's observations confirmed what other telescopes hinted at. A near-perfectly symmetrical coma, unchanging over hours of continuous imaging. That kind of geometric stability under solar influence is highly irregular. Even inactive comets exhibit some degree of turbulence. Here, the shape held completely. More strangely, the coma's spectral emissions weren't chaotic. They showed narrow-band vibrational modes in specific molecular ranges, especially carbon-based molecules like CO2 and formaldehyde. But the intensity ratios were too clean, too ordered, for natural outgassing. The thermal signature in particular oscillated with measurable periodicity, something no other known comet has displayed. Now here's where it gets even more unsettling. JWST's instruments detected layered emission zones, concentric thermal rings that varied in temperature by precise increments, radiating from the object's nucleus. This suggests not a boiling release of ice, but a regulated emission process. It's almost as if the object were venting in measured pulses, releasing gas at intervals too smooth to be random. And while those patterns were enough to raise eyebrows, the real shock came from the deep infrared mapping of the nucleus itself. JWST measured albedo contrasts, differences in how the object reflects or emits infrared light, and what it found was completely unprecedented. The object's surface is not consistent. Some regions are rough and dark, as expected, but others are unnaturally smooth, with reflectivity that hints at metallic or engineered surfaces. The transition between these regions wasn't gradual, it was sharp and boundary defined. Naturally, this triggered a wave of quiet internal debate. Was JWST seeing surface layering from a unique cometary crust, or something not geological? Officially, NASA has not commented. The JWST science team has released no formal papers on the observation, even though it would qualify as a top-tier discovery. This silence has not gone unnoticed. Multiple researchers have noted that while the data is visible in the JWST archive, key interpretive files are missing, and request logs for the observation window were scrubbed shortly after upload. In the astrophysics community, this kind of absence speaks volumes. One European analyst described it as a signal without a statement. Another, more bluntly, they saw something. They know it's not natural, and now they're stalling. Because if JWST, the most advanced eye humanity has ever launched into space, just captured direct structural evidence that 3I-ATLAS is not entirely natural, that would mean rewriting the boundaries of planetary science, astrophysics, and perhaps even civilization itself. We are no longer just looking at a mysterious object. We may be witnessing a technological relic passing silently through our solar system. And JWST may have just become the first witness, even if it's not yet ready to speak. For decades, comet researchers have relied on spectroscopy to decode the invisible chemistry of space objects. Different compounds, when excited by sunlight or internal energy, emit light at specific wavelengths, a kind of spectral fingerprint. Water vapour, for instance, shows strong ultraviolet lines. Carbon monoxide glows faint blue. Methane creates ghostly green signatures. But then there's the red glow. It's rare, subtle, and when it appears in a comet's coma, it always prompts closer inspection. In the case of 3I-ATLAS, that red glow wasn't just present, it was dominant. High-resolution optical and infrared imaging from both ground-based telescopes and spaceborne platforms revealed a soft, persistent crimson hue radiating from the outer layers of the coma. Not the blazing red of ionized hydrogen, but a darker, richer red, like smouldering embers behind frosted glass. It appeared in every exposure window between 650 and 750 nanometers, overlapping the known spectral zones of organic compounds. This was the first major clue. The colour matched known emissions from polycyclic aromatic hydrocarbons, PAHs, complex organic molecules that are considered precursors to life. PAHs are commonly found in interstellar dust, meteorites, and the dense regions of molecular clouds. But they are extremely rare in comets, and when they do appear, they're usually faint, mixed in with dozens of simpler volatiles like formaldehyde, ethane, or acetylene. But 3I-ATLAS was different. The glow wasn't faint, it was central to the object's visual identity. And here's where it gets even more intriguing. The red glow didn't fade with distance from the sun, as would be expected if it were caused by UV excitation or heat-driven outgassing. Instead, it deepened as the object approached the 2 AU mark, peaking just as it entered a tighter solar radius. This implies the compound responsible wasn't being broken down by heat, it was being activated by it. Spectral analyses showed complex absorption features that matched laboratory simulations of tholin-like materials, organics formed when ultraviolet light interacts with nitrogen and carbon-rich ices. These substances don't just glow, they retain thermal energy, releasing it slowly over time, which could help explain the stable heat emissions previously detected in the JWST data. Now here's the deeper implication. If these compounds are truly Pey's or Tholin variants, it confirms that 3I-ATLAS is carrying complex carbon chemistry, the kind we associate with prebiotic materials. Not only that, but the distribution of these compounds across the coma was even and symmetrical, indicating they weren't simply randomly embedded dust. They appear to be layered or embedded in structure, possibly protected beneath the surface for eons before being released under controlled conditions. That last part matters, because in nature, patterns usually form from chaotic processes, lightning strikes, stellar explosions, or the high-energy chemistry of deep space radiation. But in 3I-ATLAS, there's no evidence of a chaotic release, no explosive vents, no dust clouds, no asymmetric plumes, just a slow, consistent radiation of red light, a controlled release of organics. So, what are the theories? Some researchers suggest that the object passed through an organic-rich interstellar zone, accumulating a dense carbon layer on its surface. Others propose that the red emission comes from internally synthesized organics created by a combination of trapped gases and cosmic ray exposure, a kind of slow cooking of molecules inside the object's crust. But a quieter group of analysts has begun to suggest something more radical, that the glow is not just a chemical echo, but a signal. The red frequencies seen in 3I-ATLAS's emissions fall within communication windows used by deep space transmitters. The regularity of the output, combined with the molecular complexity of the compounds involved, has prompted comparisons to designed radiative materials, the kind used to broadcast presence, not merely reflect it. Whether natural or not, the message is clear. 3I-ATLAS is not just a rock in motion. It's carrying the molecular language of life and speaking it in red. In orbital mechanics, silence is deceptive. Space may be void of sound, but it's never still. Comets tumble, objects drift, solar winds nudge, gravitational tides pull. Every celestial body responds predictably to the forces acting upon it, unless, of course, it doesn't. That's what happened with 3I-ATLAS. Between November 12th and November 14th, astronomers tracking its path noticed a deviation, a small but significant change in its orbital trajectory, barely a blip in the ephemeris at first, but one that compounded over the following 48 hours into something far harder to ignore. The object had shifted, not dramatically, not chaotically, but deliberately, as if responding to a quiet instruction, rather than a random force. This wasn't the first deviation in 3I-ATLAS's journey, but it was the most precise. It occurred at a point in the object's solar approach when the surrounding forces were minimal. Solar pressure was low. Earth's gravitational influence had already passed. No planetary bodies were nearby. And yet the object executed a micro-arc correction of approximately 0.003 degrees, resulting in a downstream position shift of nearly 70 kilometers, enough to subtly realign its heading toward the inner solar system corridor near Mars. Naturally, mission analysts and orbital modelers were cautious. Could this be an artifact? A misreading of telescope data? A false positive? But 3 separate observatories, in Chile, South Africa and Japan, confirmed the same thing. The object's trajectory had altered mid-flight, without any visible external trigger. Here's why that matters. In the history of cometary science, spontaneous orbital corrections only occur under 2 conditions. 1. When an object ejects mass violently, such as during fragmentation events. 2. When sustained outgassing from sunlit surface vents gradually nudges its path. Neither of those were observed. There was no flare, no tail divergence, no sudden brightness spike. In fact, the coma remained as stable as ever, smooth, spherical, unbroken. If the object had vented material to adjust its path, there should have been visual turbulence, a measurable dust wake, or spectral signs of gas ejection. There were none. This silent correction left scientists with an uncomfortable question. How did it move without pushing against anything? One possibility is that 3I-ATLAS harbours internal mass redistribution. In spacecraft dynamics, moving internal components, like reaction wheels, can adjust attitude or vector without expelling propellant. If 3I-ATLAS contains dense core segments that shifted internally, the resulting momentum transfer could create a subtle course change, but that requires a level of engineering, not randomness. Another idea floated in private technical briefings is that the object may have used a form of magnetoplasma propulsion, utilising solar wind particles and electromagnetic fields to create controlled drift. Again, this is theoretical tech still being tested on Earth, not something nature has been observed to use on its own. A third theory, perhaps the most speculative, is that the object is autonomously navigating, responding to solar flux variations, gravitational nodes, or interplanetary magnetic field conditions using unknown principles, essentially behaving like a slow-guided probe, adapting its path with intelligence, not instinct. NASA, when asked for comment, gave a neutral reply. Trajectory models are continuously refined based on available photometric and astrometric inputs. Minor variances are within expected tolerances. But this wasn't minor, it was surgical, and it was silent. The implications are staggering. A comet shouldn't be able to make mid-flight course corrections, yet 3I-ATLAS did, without shedding mass, without detectable force, and without the natural chaos that follows most spontaneous changes in velocity. Whether it was a response, a triggered event, or something embedded deep within its structure activating at the right moment, one thing is clear. The laws of physics weren't broken, but they may have been used, and that's something comets don't normally do. Pilots do. While 3I-ATLAS has dominated headlines with its visual anomalies and orbital deviations, a second, quieter story has been unfolding in parallel, one that may be just as important. It begins with a curious glow captured not by telescopes on Earth, or by the James Webb Space Telescope, but by an often overlooked instrument aboard an aging satellite, SWAN, or the Solar Wind Anisotropies camera on board the SOHO spacecraft. SWAN's mission is simple: map the distribution of Lyman alpha emissions from hydrogen atoms in space. These ultraviolet emissions are invisible to the naked eye but incredibly useful for detecting water vapour in comets, which breaks down into hydrogen under solar radiation. When a new comet releases water, SWAN sees it long before it brightens in the visible spectrum. And in early November, it saw something strange, but not exactly from 3I-ATLAS. Instead, the source was offset. It originated several arc-minutes away from the comet's known position. At first, analysts assumed it was a calibration error, a software artifact or background hydrogen noise, but the signal persisted, and over the next 5 days it moved, trailing behind 3I-ATLAS like a ghost companion. Eventually, researchers began to refer to it informally as the SWAN object, unsure whether it was a fragment, a secondary body, or something even stranger. Here's where it gets more compelling. The hydrogen emissions were too strong to come from a simple icy fragment. The Lyman alpha intensity suggested the presence of complex outgassing, yet there was no visible coma, no dust trail, and no thermal glow on infrared scans. In essence, it was invisible, except in SWAN's narrow detection window. That's highly unusual. Hydrogen doesn't travel far unaccompanied. It's light, reactive, and easily dispersed by the solar wind. For it to maintain coherence, it has to be emitted continuously and shielded, or replenished, through a controlled release mechanism. And yet, the SWAN object maintained a stable hydrogen cloud for over a week, hinting at internal reservoirs or systems designed to regulate its emission. When analysts overlaid the motion paths of 3I-ATLAS and the SWAN signal, they noticed something else: synchronization. The two objects, though visually disconnected, maintained a consistent angular velocity and vector offset, adjusting in tandem as they moved through the inner solar system. It's as if one were shadowing the other, or perhaps guiding it. Natural debris doesn't behave like this. Fragmented comet pieces diverge rapidly due to solar radiation pressure and mass differences. But these two bodies were coordinated. That raises a chilling possibility. What if the SWAN object is not debris at all, but a second body, active, silent, and designed to remain hidden? Some in the research community have started to compare this behaviour to a binary probe architecture, where one object acts as the emissive decoy, drawing observation, while the other plays the role of a stealth controller, gathering environmental data, scanning planetary fields, or even relaying communication through exotic low-energy emission modes like hydrogen Lyman alpha, which are difficult to detect except by dedicated instruments like SWAN. One theory suggests the SWAN object could be a thermal regulator, absorbing and diffusing radiation, creating a buffer zone behind 3I-ATLAS to stabilise its tail geometry. Another, more speculative idea proposes it's an information probe, riding in the shadow of the larger body to observe our reactions, detect transmissions, and map signal reflections from Earth's satellites and observatories. Whatever it is, it's no longer deniable. The Swan signal is real, moving, and coordinated with 3I-ATLAS. And if its signature tells us anything, it's that we're not looking at a solitary traveller. We may be witnessing a pair, working together in silence, drifting through our system, with a purpose we don't yet understand. One visible, one hidden, both watching. In the age of open data and live-streamed rocket launches, it's easy to assume we see everything, especially when it comes from NASA, ESA, or observatories with public funding. But space agencies, like any large institutions, have filters. And with 3I-ATLAS, those filters were working over time. When the first high-resolution images of 3I-ATLAS began to circulate in early November, they came through the usual channels: public-facing dashboards from the European Southern Observatory, selected amateur astrophotographers uploading to open databases, and a few curated snapshots via NASA's media teams. These images were stunning. They showed a glowing, symmetrical object surrounded by a soft, luminous halo. Some frames hinted at a crystalline geometry in the coma's density field, but nothing more. They were high quality. They made headlines, but they weren't the sharpest. Because behind the scenes, higher resolution images did exist, and they were quickly pulled, rerouted, or never released at all. It started with a private leak, a compressed thumbnail posted briefly on a defunct astronomy forum. The file name included a timestamp and identifier that matched the internal cataloguing system of the Very Large Telescope, VLT, in Chile. The image, though degraded, was different from anything released to the public. It showed edges, actual edges, defined linear structures on the surface of the comet-like body. Not pixel artifacts, not atmospheric distortion, clean contours, flat surfaces bordered by shadowed ridges, the kind of geometries nature doesn't usually produce, at least not in the vacuum of interstellar space. Within hours, the post was deleted, the account banned, the IP address scrubbed, but copies of the image circulated among private astronomy circles, raising urgent questions. Why wasn't this version shared on the official archive? Why did the metadata disappear? More reports emerged. Astronomers using remote access scopes in the Canary Islands claimed that certain scheduled image captures were replaced by low-quality proxies in the shared databases. Observers from Hawaii's Mauna Kea facility noted that their longest exposure images, some captured during perfect sky conditions, never appeared in the public queue. In one case, a researcher received a direct notice from a government liaison warning that certain objects may be subject to temporary classification protocols. This isn't unprecedented. Governments and agencies have long had quiet policies that allow temporary withholding of data if it's deemed sensitive, often under the blanket of national security. Usually it involves satellites, missile detections, or space debris linked to defense programs. But a comet? Why would an interstellar rock warrant classification? One internal whistleblower, a technician familiar with the Infrared Processing and Analysis Center, IPAC, confirmed that a sequence of high-definition frames captured by the Spitzer archive sweep were flagged before final release. The reason? Anomalous geometric albedo patterns inconsistent with natural origin. Translation: reflections too perfect, in angles too consistent to be just ice or rock. Even more telling was the silence that followed. No press briefings, no clarification, no updated image sets. NASA's official gallery listed the last publicly approved high-res frame as coming from November 14th, despite multiple observatories confirming ongoing image captures for days afterward. So where did those images go? Some believe they were redirected to private analysis teams within DARPA, Space Force, or foreign aerospace partners. Others suggest they were deleted entirely, removed before any irreversible leak. A third camp, perhaps the most optimistic, believes they're being studied in silence, not for suppression, but for confirmation. Because if those sharper frames truly showed structured surfaces, rectilinear ridges, or metallic glints, the kind of evidence that points to artificial design, then the agencies weren't hiding data. They were buying time. Time to understand what we're seeing. Time to decide how, or if, to tell the public. And until that decision is made, one thing remains certain. The public saw the light, but not the detail. It's easy to think of 3I-ATLAS as something new, a sudden arrival just now entering our awareness, just now appearing in telescope feeds and daily ephemerids. But what if that perception is wrong? What if 3I-ATLAS didn't just enter our solar system, but has been inside it longer than we realise? What if the question isn't what is it, but how long has it been watching us? The earliest confirmed sighting of 3I-ATLAS, according to published orbital data, places its detection in August, a faint, fast-moving object beyond Jupiter's orbit. But that's only when it was recognised. As with many objects of interstellar origin, it's entirely possible, even likely, that it was moving through the outer solar system for months or even years without being properly catalogued. Small, dark, fast-moving bodies often evade early detection, especially if they approach from solar-blinded vectors or along the galactic plane, where noise and dust distort telescope vision. But several things make 3I-ATLAS stand out, and suggest we may have been under observation much longer than the data implies. First, the entry angle. Simulations from the European Space Agency's Orbital Integration Team show that 3I-ATLAS did not arrive on a simple hyperbolic trajectory like other interstellar visitors. Its inbound arc was bent, almost as if it had curved its way into the system rather than falling straight through it. Some gravitational bending can be explained by massive bodies, Jupiter, for example, but the bending appears to precede any close planetary encounters. That hints at pre-existing momentum changes, potentially controlled manoeuvres, long before Earth even saw it. Second, there are the radio anomalies. In early July, several deep space listening arrays, including CHIME in Canada and Meerkat in South Africa, logged transient radio bursts at frequencies that didn't match known pulsars or fast radio burst signatures. These emissions weren't intense enough to make headlines, but their repeating pattern and sky location were flagged for later review. Only later did scientists realise those signals came from roughly the same sky coordinates where 3I-ATLAS would later emerge. Were those radio pulses a coincidence, or were they an early ping? Third, there are old images. After 3I-ATLAS was officially logged, dozens of observatories around the world began conducting pre-covery searches, looking through archival telescope data to see if the object had been unknowingly imaged in prior months, and it had. A surprising number of archived exposures, probably from as far back as March, show a faint object in the exact expected trajectory, moving slowly across starfields. But the most curious of all came from a solar observatory in Thailand, which had been capturing full-dome ultraviolet snapshots for ionospheric studies. One of its March 28th frames contains a sharp point-source glow where no known object should have been. Cross-referenced against orbital reconstructions, it perfectly aligns with 3I-ATLAS's predicted path, meaning it was already watching from deep space 8 months ago. So what does all this mean? It suggests that 3I-ATLAS didn't just appear, it positioned itself, that it may have been entering quietly, and more importantly that it was already collecting, long before it was collecting attention. What would it be observing? Our satellites, our emissions, our planetary radio noise, the pulse of Earth's electromagnetic bubble, even our reactions to its appearance, how fast we noticed, what we said, how we described it. If this is true, if this is not just a rock or a comet but a deliberate presence, then it's not here to introduce itself, it's here to listen. And it may have been doing so for much longer than we think. We've grown accustomed to what a comet is supposed to look like: a rocky or icy nucleus, a glowing coma, and a long tail of gas and dust streaming away from the sun. It's not just expectation, it's physics. Solar radiation and solar wind interact with volatile materials on a comet's surface, forcing out particles that form visible trails. The brighter the sun-facing side, the more dramatic the tail. But 3I-ATLAS challenges this entire model, not by lacking a tail, but by masking it. And it leads us to ask a question that flips our assumptions. What if the tail was never meant to be seen? When 3I-ATLAS was first observed, astronomers noted something strange: a perfectly rounded coma, symmetrical in all directions, with no clear tail extending outward. Even as it approached the sun, its brightness increased, but its morphology remained static. There was no directional streaming of dust, no obvious reaction to solar wind, no typical formation of ion tail or dust tail, both of which should be present in a highly active object this size. The tail wasn't missing, it was hidden. Infrared instruments later picked up hints of elongated thermal signatures trailing behind the object. Not glowing, but warm. Not bright, but structured. This meant something was extending behind 3I-ATLAS, a structure or emission, but it was invisible in the optical spectrum. Why? One answer lies in wavelength manipulation. Certain materials, particularly synthetic polymers, nanostructured surfaces, or electromagnetic field envelopes, can be engineered to suppress specific wavelengths of light. Essentially, they create a kind of cloaking effect, redirecting or absorbing visible photons while allowing thermal or radio emissions to pass through. If the tail of 3I-ATLAS consists of engineered particles, or worse, of a non-material energy field, then it would not scatter light the way typical comet dust does. To our visible telescopes, it would seem non-existent. To our infrared sensors, only faintly present. To sensitive spectrographs, perhaps even deliberately misleading, tuned to mimic cosmic background noise. In short, it's not that there's no tail, it's that we were never meant to see it. This would explain several anomalies. First, the lack of forward-facing light distortion. Normally, light from stars behind a comet's tail appears reddened or diffused. That hasn't happened here. Background starlight passes cleanly through the space behind 3I-ATLAS, as if nothing is there. Second, the polarization irregularities. When astronomers analysed scattered light from the coma, they found inconsistent polarization vectors, suggesting the presence of field interference, possibly from electromagnetic modulation. Some even speculate that the tail is being compressed electromagnetically, held in place by a toroidal field that prevents dispersion. But perhaps the most important clue is what lies within the hidden tail. Multiple deep space-listening arrays, including Japan's Hitomi Array and the Indian Sarov system, detected oscillating low-frequency emissions trailing behind 3I-ATLAS. These weren't bursts. They weren't random. They were tonal, narrow-band emissions with slowly drifting harmonics, almost like sonar pings, stretching out in a direction only infrared and radio could follow, and they were aimed away from Earth. Which brings us to the heart of this theory. What if the tail isn't an accidental consequence of solar exposure, but a functional component, a shield, a transmitter, a sensor array, something designed not for show, but for functionality, operating silently in the background, while our attention stays focused on the glowing coma? If that's true, then the entire idea of a comet tail needs to be reconsidered, not as a passive reaction, but as an intentional design, a signature not for us to see, but for something else entirely to receive. It wasn't a grand explosion. It wasn't a sudden shift in brightness. It was just one frame, one still image, taken in the early hours of November 27th, that quietly shattered everything we thought we knew about 3I-ATLAS. Captured by a high-speed imaging telescope at the Pic du Midi Observatory in the French Pyrenees, this frame was supposed to be routine. Part of an automated sweep, it was one in a series of thousands, stacked to track motion and structure over time. Nothing unusual was expected. In fact, the session had been written off as low priority due to slight atmospheric turbulence and cloud cover in surrounding regions. But in this frame, this one frame, something changed. A sharp, angular protrusion emerged from the body of 3I-ATLAS. It wasn't a dust flare, it wasn't thermal bleeding, it was rigid, uniform and symmetrical. Measuring nearly 20% of the object's total width, the structure extended laterally from the nucleus, like a blade unfurling from deep within. The material contrast was stark. The main body of 3I-ATLAS glowed faintly, like expected cometary matter, but this extension reflected light in a way that screamed metallic sheen, linear reflectivity in two spectrums. At first, technicians assumed it was an imaging artifact, a glitch caused by lens diffraction or CCD noise. But multiple filters captured the same anomaly at identical coordinates. A second observatory, La Palma, in the Canary Islands, confirmed a matching shape in the same minute, using a different optical system entirely. It was real, and within the next 15 minutes, it was gone. Subsequent images showed nothing but the original symmetrical coma. No flare, no structure, no evidence of change. But that single frame, that one ghostly snapshot, had already been seen by too many to ignore, and it was too clean to dismiss. So what was it? Some speculated it was a deployment, a panel or sail emerging temporarily to adjust orientation or gather energy. Others believed it to be a sensor arm, extending briefly to scan local solar wind or magnetic fields. A few theorized even darker possibilities, a release mechanism, dispersing something into space, or a communication relay, transmitting a burst message timed to a specific alignment between Earth, the Sun, and deep space. What makes this event even more unsettling is what happened after. In the hours following the frame's capture, three things occurred. NASA's Solar Dynamics Observatory, SDO, issued a sudden recalibration alert, citing solar reflectivity interference from an unnamed body crossing its viewing corridor. The timing and trajectory matched 3I-ATLAS perfectly. The European Space Agency's Deep Space Antenna in Cebreros reported telemetry anomalies, while tracking a Mars-bound probe, brief signal delay and phase disruption, which vanished within minutes, coinciding precisely with the structural emergence. China's Chang'e 6 lunar orbiter detected a series of narrow-band microwave pulses directed not from Earth, but from the outer solar system, triangulated roughly along the extended tailpath of 3I-ATLAS. These were not coincidences. The last frame, that frozen moment, was not a glitch, but a trigger point, a shift in status. The moment something inside or around 3I-ATLAS made its move. Whether it was to align, to deploy, or to send a signal, one truth became impossible to deny. It had a next phase, and from that moment forward, every observatory treated it differently. Not as a comet, not as a visitor, but as a participant. Because in that single image, the illusion of passivity was shattered, and we were no longer just watching it. It was doing something, and the question now isn't what it is. The question is what happens next.